Okay, so in this section, we are talking about the limit laws, and we're going to start computing limits using these, which means we're computing them algebraically instead of using a graph like we have been. So I'm just going to go ahead and write down all of the laws. They're not in the same order as you find them in the textbook. So whenever I'm referring to them by the number, I'm referring to this particular list, the order that I put it in. Okay, so first off, the limit of a constant so if you had the limit as x goes to a of c, where c is a constant, the limit of that is just equal to c. And you can see this by thinking about the say we had the function f of x equals c, or here I'll write y equals c. And so your function is just a straight line, a horizontal line, and no matter what a is, you can see that the function value is always going to approach c because it's just always c in the entire domain. Okay. Also, the limit of x. So if we have the limit as x goes to a of just x by itself, then that is going to be equal to a. And again, you can think of the graph. So the line y equals x, let's straighten that out a little bit. Looks like this. Here's y equals x, and whatever a is, the value of the function at a is also a, right? So in this case, the limit as x goes to a of x is equal to a. Okay, so those are pretty basic. Now the other ones are things that you would like to be true, and it turns out that they are actually true for limits. So first off, if you have the sum of two functions, so if you have, say you want to take the limit as x goes to a of f of x plus g of x. Now, assuming the limits of each of those exist, so that is up here. I did write this here, but I didn't mention it. So c, the lowercase c is a constant, and we're assuming that the limit as x goes to a and the limit as x goes to a of, the limit as x goes to a of f of x and the limit as x goes to a of g of x, that those both exist. Okay. So if that is the case, then we can just split this, and this is equal to, if we just take the limits separately and then add them together. So x goes to a of g of x, like that. Okay, and then similarly, if we have the difference of two functions, so the limit as x goes to a of f of x minus g of x, then that is the limit as x goes to a of f of x minus the limit as x goes to a of g of x, like that. Okay, and also if you have, so I've been writing the names. So here, if you have a constant multiple, meaning you have the limit as x goes to a of the constant times the function, then you can pull it outside of the limit. So I would think of this as bringing this constant out front. So that's the same as c times the limit as x goes to a of f of x. Okay, if you have multiplication, so if you have two functions being multiplied together, here we do need to make sure that, so this is true if both of the limits are finite. So there is a particular situation in which we can't do this. This is broader than the exact situation, but we'll talk about it later. It actually won't come up for a while, but when we get to L'Hopital's rule, I will talk about this again. But this will always work if both of the limits are finite. If that is the case, then we have that the limit of f times g is equal to the limit of f times the limit of g. Right? That's a little messy, so there we go. Okay, and similarly with division, here we also have a condition, and that is so long as the limit of the function that's in the denominator, so I'm going to use g of x for that, if that's not equal to 0, then we can say that the limit of f of x over g of x is equal to, make this a little smaller, limit of f over the limit of g. Right? So we can do that so long as we don't get 0 in the denominator, right? Okay, and then the last two are about the nth power and nth root. So in both of these cases, these, when I refer to n is a positive integer. Integer. Okay, now, okay, so the first one, the nth power, that's saying that if we have the limit as x goes to a of our function f of x to the power n, then that's the same as the limit as x goes to a of f of x. So we take the limit and then we raise that thing to the power n. Okay, and then similarly, if we have the limit as x goes to a of the nth root of f of x, like that, that's the same as the nth root of the limit as x goes to a of f of x. Okay, so long as this is assuming that the limit is greater than or equal to 0 if n is even. Right, so we can't take a even nth root of something that would be negative. So assuming that that's all fine, then you can pull the nth root outside of the limit and then take the limit of the function and then apply the nth root. Okay, so those are all of the limit laws. So we are going to go ahead and use them. So in the next problem, so what I want, if I say something like this, evaluate the following limit, justifying each step with one of the limit laws, that means that you're going to break this down into pieces very slowly and make sure that you label each step with the law that you're using, right? Okay, so I will do an example of that. Okay, so here, the first thing I'm going to do is I can split this into two functions that are being added together, so I can sort of group them like this. So, let me zoom out a bit so that I can see. So I'm using the third limit law, so I'm going to put a 3 above the equals sign. and then I'll split this into the pieces 4x squared minus 2x plus the limit as x goes to 2 of just 3, right? Okay, now I think I'll go ahead and deal with this piece first. So this is the limit of a constant, right? So I can use rule 1 to say that that limit is equal to 3. So using the first rule, I get, so just to be clear, this is the limit as x goes to 2 of this piece plus the number 3. And then I'm going to use the difference rule to split this into two functions. So that is the fourth limit law. Okay, I will have 4x squared minus limit as x goes to 2 of 2x and plus 3. Okay, now both of these have constants, so I'm going to use the constant multiple rule to pull those constants outside of the limit. So here I'm going to pull this 4 out, and I will get 4 times the limit as x goes to 2 of x squared. And then I will have 2 times the limit as x goes to 2 of just x. Right? Okay, now we're almost there. This is x to the power 2. So if I use the nth power limit law, so that's number 8, I can write this as the limit as x goes to 2 of x to the power 2. I'm going to leave that one alone for now, so the rest just stays the same. And then now we have 2 limits of just the function x, right? So using the second law, that is equal to 4 times, this is just going to be 2, right? That's squared, and then we get 2 times 2 plus 3. Okay, so you can see we did this very slowly, right? Because we only used one law at a time. If you have done limits before, this probably seems very slow and tedious, but it is what I would want you to do if I asked this type of question, so justifying each step, right? Just to show that you know exactly where you are using each law, right? But we'll have some rules that I'll go over later that'll make this faster. Okay. But let's do one more example. So here we have this function, and the first thing that we would want to do here is probably use the division rule. But before we do that, we need to make sure, so remember that we need to have the limit of the bottom, or the denominator, is not equal to 0, right? So first we check that this limit as x goes to minus 2 of the denominator, so 5 minus 3x, does not equal 0. Okay, so we're going to do this off to the side before we start doing any calculations. Okay, so I'm going to go ahead and label each step with the limit law as well down here. Okay, so we have this, and first thing we want to do is split it. So we're going to use the difference law. So that will give us limit as x goes to minus 2 of 5 minus the limit as x goes to minus 2 of 3x. Right. Okay. Now that 5 is a constant, so by the first limit law, that is just equal to 5. And then we copy down the rest. Now we can use the constant multiple rule to pull that out. So I believe that's number 5. Let's double check. Yeah, constant multiple. Okay. So we get 3 times the limit as x goes to minus 2 of x. And then we use the second rule, which tells us that the limit as x goes to minus 2 of x is just minus 2. So here we get 11, which is not equal to 0. So that means that up here we can go ahead and use our division rule. So that should be number 7. And so that law tells us that this is equal to the limit as x goes to minus 2, so I'm going to mark that off, of x cubed plus 2x squared minus 1 over okay, and then we already computed the bottom limit, so I'm going to go ahead and write that in. So this will be over 11, and then the top just stays the same. It's 2 minus 2. Right. Okay, and then we are going to just do this essentially the same thing for the numerator. I'm going to use both the sum and difference rule at the same time, so I'm just going to write 3 and 4. Well, maybe I shouldn't write it plus because that makes it seem like it's 7. So 3 and 4. Okay, which means I get the limit as x goes to minus 2 of x cubed plus the limit as x goes to minus 2 of 2x squared minus the limit as x goes to minus 2 of 1. Okay, now the next thing I'm going to do is just take the limit of this constant. So by the first rule, I'm actually going to cheat and copy this. Oh, okay, never mind. That might take longer than I thought it would. Okay, I will just copy this down. Okay, so we get, and just so it's clear, this is minus 1 over there, over 11, and then let's go ahead and pull out this constant multiple, so that's rule number 5. Is to minus 2 of x squared. Okay, and then we need to use the nth power rule. We'll use it on both of these limits. So I think that is number, which one is that? That is number 8. Okay, so by limit law 8, this is equal to limit as x goes to minus 2 of x cubed, 2 times the limit as x goes to minus 2 of x squared, and then over 11. And then now we're, oh, oops, that should be the limit of x squared. Okay, now we just need to use the second law to say that this is equal to, so this limit here is equal to negative 2, and so is, well, this is the same limit, so also equal to -2 minus 1 and over 11, and now we're done. We just need to simplify. Great, so this would give us -8 plus 8 minus 1, so it's -1 over 11. Okay, so, right. Basically, when we are doing these limits, so after we broke it into two pieces, this basically became a limit of a polynomial over a limit of a polynomial. And generally, when we do find the limit of a polynomial, it always goes the same. So we just break it into each piece. So this is a sum of the different terms, right? So we just break it into a different limit for each term, and then we pull out all of the constant multiples, and then we use the nth power rule to put all of the exponents on the outside of the limit, and then we use the second rule, which tells us how to take the limit of just x, right? So it always goes the same way. So we are going to just make a generalization that says that if f of x is a polynomial, and in fact, also if f of x is a rational function, so when I say a rational function, this means a ratio of two polynomials, so it's just like this function right here. So this is a ratio of two polynomials is called a rational function. Okay, so if we have a polynomial where we have a rational function such that okay, I will put it this way, such that direct substitution does not make the denominator 0. Then we can directly substitute. So I didn't exactly tell you what direct substitution is, but hopefully it will be very clear in 1 second. So then we can directly substitute, and all that means is we just plug in, so if we have the limit as x goes to a of the function, we just plug in the actual point. So we just evaluate f at a. So meaning just plug in x equals a, right? Okay, so when we do this example, hopefully this is pretty clear. So we have here a rational function, so we have a polynomial over a polynomial. If we plug in x equals 2, it doesn't make the denominator 0, right? We would get 4. So that means we can go ahead and directly substitute, and so we just plug in 2 wherever there's an x. We get 2 times x. We get 2 times 2 squared plus 5, and then we get 2 plus 2, which is going to give you 13 over 4, right? So pretty easy. I mean, there's a lot of words here, but actually using it is pretty straightforward. Okay, so we're going to do some more examples in the next video.